Have you ever looked at a computer's specs and wondered, why are there two different kinds of memory? You've got this small chunk of really fast RAM, and then this giant but slower hard drive. It almost seems inefficient, right? Well, today, we're going to pull back the curtain on the surprisingly smart reason behind this whole setup.
Okay, so let's just get right to the heart of it. When engineers design a computer, they're wrestling with this constant puzzle. We, the users, want everything. We want it to be unbelievably fast, we want it to hold all of our data, and of course, we don't want it to cost an arm and a leg. The problem is, in the world of memory, you just can't have all three at once.
And this brings us to what we can call the memory dilemma. See, the computer's processor, its brain, operates at incredible speeds, thinking in nanoseconds. But our digital lives, our photo collections, our video games, all those huge files, they need massive, massive amounts of space to live in. And here's the kicker. The memory that's fast enough to keep up with the CPU just isn't big enough to store all our stuff.
So this is the fundamental trade-off right here. You can get memory that's lightning fast, or you can get memory that has a ton of capacity. But getting both in one package, it's technically possible, but it would make our computers so ridiculously expensive that almost nobody could afford one. And that's exactly why we can't just have one single type of memory that does it all. So what did the engineers do? They got clever. Instead of trying to build one perfect do-it-all memory, they created this really elegant compromise, a three-tiered system where each level is specially designed for a very specific job.
And this image right here shows that solution perfectly. You can see how the memory is broken up into these three main categories: secondary, primary, and all the way at the top, internal process memory. Now look at those arrows down at the bottom. As you go from left to right, from the big, slow storage to the tiny, fast internal memory, the speed goes way up, and so does the cost. But the size, the capacity, it drops dramatically. It's like a pyramid of trade-offs.
You know, a good way to think about this is like you're hiring athletes for different events. At the top, you've got internal memory. That's your sprinter. Unbelievably fast, but only for a very short distance. It's got low capacity and it costs a fortune. Way down at the bottom, you have secondary memory. That's your marathon runner. It's not going to win any sprints, but it can go on forever, holding a massive amount of data for a really low price. And primary memory, right in the middle? Well, that's your middle distance runner, trying to give you the best of both worlds. All right, let's climb to the very top of that pyramid and see how this all works. We're going to start with the fastest tier of them all, the memory that's basically the CPU's immediate, short-term brain.
This is internal process memory. A good analogy is to think of it like the thoughts that are in your head right now. It's not for storing memories from your childhood, it's for what you're actively thinking about this very second. The processor needs this data instantly, and its location, right next to the CPU, is what makes it so incredibly quick.
So what's really wild here is that this memory is often physically built right into the CPU itself or sits just millimeters away. That's the secret to its speed. But that incredible performance in prime real estate comes at a huge cost, which is why it has such a low capacity. We're talking mere megabytes. You've probably heard these terms thrown around before, like cache memory, L1, L2 cache, and CPU registers. This is what they are.
Okay, so let's take one step down from the CPU's immediate thoughts. Now we're at the computer's active workspace, or its workbench. And this is the memory that most of us are actually familiar with.
This is primary memory, and you almost certainly know it as RAM. Think about it. When you open an application or a file, it has to be pulled from your slow, long-term storage and put somewhere the CPU can access it quickly. That somewhere is RAM. It's the temporary holding area for every single thing you're currently working on. Now, primary memory really comes in two main flavors. The one we talk about most is RAM, and it is volatile. And that's just a technical way of saying that when you shut off the power, poof, everything inside it disappears. It's like a temporary notepad. But then you have ROM, or read-only memory. This stuff is non-volatile, meaning the data sticks around even with no power. And it has one absolutely critical job: to hold the permanent instructions, the BIOS or UEFI that tell your computer how to wake up and get started in the first place.
And finally, we get to the foundation of our memory pyramid. This is the huge, long-term storage system. This is your computer's permanent digital library.
You know, the source material we're looking at really puts it perfectly. Secondary memory is all about one thing: permanence. This is where all your files, your operating system, and all your applications live when you're not actively using them. So when you see a computer advertised with a 1 terabyte hard drive or a 512 gigabyte SSD, this is what they're talking about: secondary memory.
Just think of it like a massive library. It holds everything you own, but it takes a little bit of time to walk over to the shelf and pull out the specific book you need.
And if you look at its characteristics, it's the total opposite of internal memory. We get massive capacity for a super low cost, but it's way, way slower. And here's the most important detail. The CPU cannot work with data directly from here. It's just too slow. That data has to be copied over to the workbench, to primary memory, or RAM, first. And this is the category where your classic spinning hard drives and their much faster modern cousins, the solid-state drives, or SSDs, belong.
Okay, so we've got these three totally different tiers of memory. How on earth do they all work together to give us that smooth, seamless experience we expect from our computers?
Well, it all comes down to this really simple three-step dance. First step, fetch. When you double-click that icon, your computer fetches the program from the slow but huge secondary memory, your hard drive. Step 2, load. That program is then loaded into your much faster primary memory, your RAM, which is the active workbench. And finally, step 3, process. The CPU grabs the most critical little bits of data it needs right now and pulls them into its own super fast internal memory, its cache, to do the actual work. It's a flow from the library to the workbench to right inside the brain.
So at the end of the day, this whole memory hierarchy, it isn't some flaw or clumsy workaround. It is an incredibly clever and elegant solution. It's a beautifully balanced compromise that gives us the best of all worlds. We get amazing performance, we get huge storage, and we can actually afford it. This system is what makes modern computing possible.
And that brings us to a really fascinating question to think about for the future. As technologies like those super fast SSDs start to blur the lines between these different tiers, will we ever conquer these trade-offs completely? Is it possible that one day we could have a single, universal memory that's as fast as cache, as big as a hard drive, and is still affordable? It's definitely something to think about.